Hello everyone. So today we are going to analyze the time complexities of few of the algorithms. We'll be understanding all the time complexities which are there. So it is going to be a handbook for all of you, okay? So let us begin. Now the first thing I want to show you is this constant time complexity, okay? Which is basically known as big O of 1, okay? Now this algorithm is often used whenever, let us suppose, you want to access a specific element in an array, or you want to insert or delete something at the beginning of a linked list. There can be more basic arithmetic operations where this can be used, like you can say a plus b, or you can say a greater than b. So all of these things actually take somehow a unit complexity, okay, which is basically big of 1. Or you can also use it for something like as hash tables, okay. Now let us analyze. So you'll be able to see this code, right? So it is basically a simple code, a simple function which is returning a value which is 5, right? So how much time it will take? It will take one time, and hence it will be taking a total of big of one time, okay? Now we are having this problem. You can see what we are doing. Instead of just returning a number, we are actually returning a value of an array, right? We are basically returning the value of this array 0 index, right? Which will take 1 unit. The total time complexity will become big of 1, okay? Now we are having similarly one more problem. You'll be able to see this one. It is accepting two numbers a and b, right? And then it is basically adding those both two numbers, and then it is returning the value, right? How much time will it take? It will take 1 unit of time, because this addition will take 1 unit of time, and then it will be returned, right? Similarly, you'll be able to see this one, right? So what it is doing, it is basically checking whether number is a even number or not. So this will also take 1 unit of time, which will basically result in big of 1 unit of time, okay? So this were the 4 problems. Hopefully you were able to understand this. Let us move on. Now the next time complexity is basically logarithmic time complexity. This time complexities you will be often able to see in binary search, or let us suppose you want to find an element in a balance search tree, or certain divide and conquer algorithms like merge sort and quick sort often use this one, okay. So let us see how we can analyze this one. So we are having a problem over here which is basically a binary search problem. It is accepting two values, which is an array and a target. Now here you'll be able to see that we are initializing left and right with 0, which will take 1 unit, and then there is so we are saying left is equals 0 and right is equals length of array minus 1, right? So a total of 2 unit over here. Now this is a while loop, right? This is a while loop. Now how much time it will take? It will completely depend upon the left and the right value, how we are incrementing it, right? So we will be moving forward. Now this is a mid. It is basically doing nothing but dividing this values. So it is a floor division, will take 1 unit of time. This if will take 1, this will take 1, this will take 1, this will take 1, this is 1, and this is 1, right? And this will also take 1 unit time. But we are still unable to know what unit of time it will take. So we have to check how we are incrementing or decrementing right, okay. So we have to check how we are incrementing left and how we are decrementing right, right? So for left we can see we are saying mid plus 1, right? So what is mid? Mid is nothing but we are dividing the total size of the array by 2. So how much time it will take? It will going to take, somehow we can say it will be taking log n time, right? Because we are constantly dividing the array, right? So we are having the first array like this, then we are partitioning it. We are going left side, or we can go right side, completely upon us, upon the value, right? Then we are again dividing it into two part. One part we are searching, and the other part we are ignoring, just, right? So similarly it will go on, go on, go on, and give us a time complexity of big O of log n, okay. So whenever you see a division which is happening basically in a while loop or in a for loop, okay, instead of just incrementing the value, it is dividing it by half. You can simply say it is having a time complexity of log n, okay. So you'll be able to see this one, right? So this is basically a program which finds the peak element. Now how much time it is taking? 1, so it will be 2 unit of time. We don't know about this one right now. Mid will take 1, this will take 1, 1, 1, 1, and 1, right? Now let us understand how left and right are incrementing or decrementing. For left we can simply say it is saying mid plus 1. What is mid? It is nothing but dividing the total size by 2. That means if we go left mid plus 1, that means what will happen? If this was the array, now this will be searched, right? The second portion, the first portion will be ignored, right? So here also we are constantly, splitting the array into two parts and then focusing only one, right? So how much time it will take? Again, what? Big O of log n, okay? So it will also take log n time. So whenever you'll be able to see a loop, just try to find out how the values are incrementing or decrementing, okay? So like for loop, there is only one value which can be incremented or decremented. For while there are two cases, you can either increment left and make it reach right, or you can decrement right and make it reach left, okay? For either of the cases, the loop will break, right? So these are two problems. Let us move on. Now the next problem is basically linear time complexity. Now it is often, able to be seen on, let us suppose you want to iterate elements in an array or a linked list, finding maximum or minimum element of a unsorted array. Then there is linear search in an unsorted array. Then there is counting the occurrence of an element in an array. So these are the ones which, basically use the time complexity of big O of n. Let us see. So let us suppose we are having this simple code, right? So this function we are having, there is a f which will take 1, this will take 1, this will take 1, this will take 1. This will take how much time? We have to understand how we are incrementing number, right? So if we see for number, we can see that there is nothing which is happening, right? So number will be automatically taking a value from this array and it will go on. That means the incrementation will be of 1, right? That means it will take big O of n time. And for this one, 1 1 1 1 1, right? So these are the time complexities. Now how much time it will actually move? How many times it will actually move? It will move how many times this loop will be moving, right? So we can simply say n n n n, right? For this too, it is uncertain because we cannot say whether it will be learning, it will be basically going to run or not, but we assume that it will get run somehow. And for this one it will be n, right? So the total time complexity will become n plus n plus n plus n, which will nothing but it will basically say us that it will be doing n only, right? So the time complexity becomes big O of n. We ignore these constants because these are very minute and it can be ignored, okay? Now let us see this one. So it is basically a simple initialization will take 1 unit. We are having this for loop and it is doing nothing but initializing the array element one by one in num, which means it will take plus 1, right? It will be incrementing the num by 1 1 1, right? Which will make it take a time of n. Now this loops, basically this conditional statements which are if and else, this will move for n only, right? Because they are inside this loop, this will take 1. So ultimately we can simply say it will take somehow big O of n, right? Because they are inside this one. We are just assuming how many times this will be moving, but in general we say it to be 1, right? So somehow we'll be getting this one, which is big O of n. Let us move on. Now this is basically a linearithmic time complexity. You will be able to see this often for merge sort, then we'll be able to see this for heap sort, quick sort, then certain tree based operations like sorting a binary search tree. In all of these places we often use this linearithmic time complexity. Let us analyze a problem. So this is a problem of a merge sort. Let us analyze. So we are having two functions. This function is basically merge sort and this function is for merge. Both are separate. Let us analyze each one of this, okay? So this will take 1 because this is simple if condition 1. This is mid, right? So we are going to give 1 1 1, right? Now here we'll be able to see there is a recursive call. For now, because you might not be knowing recursion, you can simply consider them to be as a single loop, and you have to check what we are basically passing. So we are passing left half or right half. What is left half? It is nothing but we are basically passing the array, we can say from start to mid, and for this one from mid to end, right? So we are actually dividing the array, right? So we are actually dividing the array. That means somehow this two are going to take how many times? It will take log n. This will also take log n, right? So because they are one after another, it will be just a simple plus. This will be simply nothing but then they are calling this merge one, right? We have to find out the time complexity of this merge one after that. So we can see that it is basically having this simple one which will take 1. this will take 1. This is a while loop. We have to understand how the while loop is basically iterating. So we can say left index, and let us say how left index or right, this one is basically moving. Okay, so we are having this right index, we are just incrementing by 1, we are just incrementing by 1, right? This will also take 1 unit, this will also take 1 unit, right? So we can simply say because they are incrementing by 1, this will take how much time it will take? We go of n time, right? And we can check the next code of the same one. So it will take 1 unit, because they are going to somehow extend this one. So we can say, yeah, they will be somehow taking 1, this will be taking 1, right? Let us come back. So this side was taking big O of n, and this was taking log n. So how many time it will be taking? It will be simply taking n log n. Okay, so it will be taking n log n. So this many time it will be basically taking. So this is the time complexity of a merge sort, and this is how we can write this one. Okay, so it will be simply big O of n log n. Is it clear? So we are just removing all of this constant times, and we are not focusing on them. Okay, so let us come up. Okay, so this is the quadratic time complexity, which is basically big O of n square. It is basically seen in nested loops or selection sort or bubble sort algorithms. Okay, so let us analyze the codes. So this is a simple code which is generating Pascal triangle. It will take 1 unit, right? So this is a for loop which is doing nothing, but it is moving in this range. The range will definitely start from 0 and it will go till the number of rows. So we can simply say it will take big O of n, right? And inside this we are having one more loop. Before that we are having 1 unit of time over here. So this is doing nothing, it is starting from 1 and it is going till I, right? So for the first time I will be 0. So somehow this will be doing nothing but going till big O of n, right? So n time. This will be 1, this will be 1, this will be 1, right? So the total time complexity will be nothing but n square, right? Because they are one after another, right? So we can say simply n square. Okay, now we are having this one which is basically a selection sort algorithm. This is going to take 1 unit of time because it is just a simple initialization. We are having this loop, it will take this I will be initialized with this range value. This range will start from somehow 0, will go till n is the termination condition, right? So somehow we can say that it will take n unit of time. This will take 1, this will take again n unit of time, because we are seeing that I plus 1 till n, right? So this will be also taking n unit of time. Then this is going to take 1, 1, and this will be also taking 1 because this is a simple initialization. This n was inside this n, so we can simply say n square. Okay, so this will be taking n square amount of time. Let us move on. Now this is basically a exponential time complexity, and this is something which we should often we can say ignore, because the time complexity gradually increases a lot. Okay, so this is something you should be ignoring. Where it is used for many brute force algorithms that involves trying all the possible solutions. Then we have nev recursion algorithms without memorization. So this is something which is basically used there. Okay, so let us analyze the simple code. You'll be able to see this code which is basically doing nothing but calculating the factorial. So we are having a recursive call over here, a recursive call over here. Let us suppose this is giving us a factorial of 5, right? 5. So this will call this factorial of 4, and then this will call the factorial of what? It will call factorial of 3, right? Now this 4 will again call factorial of 3, and it will again call factorial of 2, right? Same thing for this one, factorial of 2 and factorial of 1, right? Now if we check for each level, you'll be able to see the first level you will be having 1, for this one 2, for this one 4. So you can easily construct a simple thing which will be 2 to the power 0 plus 2 to the power 1 plus 2 to the power 3, right? Similarly we can go ahead. So that's how the time complexity for this one becomes 2 to the power n. Okay, because if you take 2 as constant, then you'll be getting that one. Okay, so this is how we actually find the time complexity of this one. You can also find out this time complexities by actually calculating the the binary tree. Okay, so you can see that this is a complete binary tree, each one is having 2 of its child, right? So using that one you can also find out, right? So we can come after this one. Now the next one is factorial time complexity. Now you'll be able to see this mostly in brute force algorithms that generate permutations or combinations. Let us see a simple code. So this is a simple code, right? It will be taking 1 unit of time, 1 unit of time, because this is a simple if, this is a simple return statement. Then we are having another recursive call over here. What is it doing? It is doing nothing, but it is multiplying n with the n minus 1, right? The whatever the value will be, right? So how much time it will be taking? It will be taking factorial time, right? So we can simply say n naught, because it will be constantly multiplying itself, which will and while it will be doing it, it will be actually reducing itself, right? So it will be for n into n minus 1, then n minus 2. Similarly, it will be going on till it reaches what? Till it reaches the 0, right? Till it reaches this 0. So how many time it will be taking? N into n minus 1. Similarly, if you can do this, you will be able to find out that it will be taking nothing but n factorial time. Okay, now let us move on. So this is a quick handbook for all the famous algorithms like linear search take big of n time, binary search take big of log n, selection sort take big of n square, and you can see the remaining ones. Okay, so these are basically the time complexities of all the famous algorithms, and you can look into this to have a quick overview about all the algorithms. Like we have Fibonacci series, longest common subsequence, coin change problem, knapsack problem. So all of the time complexities are written over here. So this was all the thing which were needed to be covered today. So today what we have understood about the basic time complexities, and I've shown you how to analyze the time complexities of each one of these algorithms.